Thanks for the opportunity to present my work in ISDFS 2026. Here I'm presenting my research article, Machine Learning Driven Performance Modeling and Optimization of Probabilistic and Hardware Acceleration. So here is the agenda for the presentation. So I'll go with the abstract, then introduction. We'll move forward to literature review, methodology, and what's the results we have achieved with the article, and conclusion and the references. So here is the abstract. What is the purpose of this research is to study a machine learning framework to predict GPU performance using benchmark data from Kaggle GPU benchmark compilation dataset. Systematic processing and feature engineering are applied, followed by training for models, random forest gradient boosting, optimized gradient boosting, and multi-layer perceptron. Gradient boosting achieves the best prediction performance with R square 9998, while RMS is 4527, while MAE is 2570. Five-fold cross-validation shows consistent and stable performance with an average R square of 0.99, and error analysis indicates very low prediction errors, and especially for ensemble models. Results demonstrates that tree-based ensemble methods combined with GPU-specific feature engineering provides an accurate and scalable solution for GPU performance prediction, aiding efficient GPU selection and computational planning. Here is the introduction. So the demand for high computational power has increased, the adoption of GPU due to their massive parallelism, high memory bandwidth, and the strong software system. GPUs are widely used in high performance computing, machine learning, but growing architectural complexity makes traditional benchmarking slow and inefficient. Machine learning based performance modeling has emerged as the efficient approach to quickly and accurately predict GPU performance. The expansion of AI and ML deep learning application has further accelerated GPU because their workload requires large-scale numerical computation. Despite their advantages, gaps remain between theoretical and real GPU performance, highlighting the need for fast and reliable performance modeling method based on the traditional benchmarking. So here's the literature review and the number of articles that we looked at for the different hardware optimizations. And let me give you the initial author in here about Luet. Bayesian optimization with automated accelerator co-design. The data set and the platform is as Xilinx FPGA. Key findings: reduced resource utilization by 88 and latency by 58% with high prediction accuracy. And the limitation here is the validation on more models and hardware platform. And one more is Salomite FPGA bit Q-learning accelerator RTA7 FPGA achieved 84 to 230 times speedups with efficient hardware usage and limited to specific task. The third one, Thomson, has ML models with feature and hardware optimization, multi-core GPU CPU setup, and training time reduced up to 90% without accuracy loss, and limited hardware setups and future scaling needed. Vector Lewis and Omar, ML workload classification data center workload achieved 100% accuracy in workload classifications, need testing on diverse real workloads, and requires validation in broader real systems. And here is the methodology that used by us for this article. The data collection. The study uses GPU benchmark compilation dataset from Kaggle, which collects GPU performance results from past mark stats updated regularly. It includes key indicators such as G3D mark, G2D mark, allowing analysis of GPU performance, power consumption, efficiency, and price trends for predictive modeling. Data preprocessing. Data preprocessing ensures the dataset is consistent and suitable for model training by organizing hardware and performance attributes, preparing categorical variables, and validating feature consistency to support accurate learning. Feature engineering. Additional efficiency based features such as performance per watt, performance per dollar, total performance, and power efficiency scores are created to better represent relationships between GPU performance and energy consumption and cost, improving prediction capability. And we'll further continue into the our methodology is that label encoding categorical variables are transformed into numerical values using label like encoding, allowing machine learning models to process the hardware category attributes without relying on target based statistics. Data splitting. The dataset is divided into training and testing subset with 80-20 ratio, where 80% data is used for training while 20 isn't for the performance evaluation on the unseen data. And the data normalization. Standard scalar is applied for normalized feature values, so each feature has a mean 0 and standard deviation for 1. And the model selections, that 4 machine learning models we have selected is random forest, gradient boosting, multi-layer perceptron, and XGBoost, are employed to learn complex nonlinear relations between GPU performance data and enable comparative analysis. Here is the results and the discussions of results is that the performance comparison in table 2 shows that all models achieve high accuracy with gradient boosting provides the best results. Achieving the highest R square is 99.98%, lowest RMSC is 45 compared to random forest XGBoost and MLP. The prediction plot in Fig 2 shows the predicted values closely matching the actual GPU performance, while the residual plot Fig 3 indicates that the errors are mostly centered around zero, confirming stable and accurate model predictions. And we have other is cross validation results for GPU performance. The random forest is 99.89 and the gradient boosting is 99.95. So pretty much all of them are close to 99, but the best one is gradient boosting again with 99.95. And we have given the other performance summary for ML models for GPU performance predictions. And here is the final results, compares R square performance of different models, showing the gradient boosting achieves the highest prediction accuracy with R square value of 99.98, closely followed by random forest and XGBoost, while MLP performs slightly lower. In contrast, deep learning approaches such as 2D CNNs, GANs shows comparatively lower R square values. You can ensemble machine learning models outperform these methods in GPU performance predictions. And the conclusion and the future. The conclusion, the proposed machine learning framework effectively predicts GPU performance using hardware specific features and pre-processing with gradient boosting, achieving the highest security accuracy about R square 9.99, demonstrating a strong precision and reliability. Despite high performance limitations exist due to reliance on benchmark dataset, possible inconsistency in user submissions, and lack of real-time performance factors such as thermal behavior and workload variations. Overall, the framework provides a scalable and cost-effective alternative to traditional benchmarking for GPU performance analysis and prediction. And the future work studies can incorporate real-time telemetry dataset, includes newer GPU architecture to improve model generalizations and predictable applicability. Additional ensemble and deep learning models such as Light LGBM, CatBoost, CNN, or transform-based approach can be explored using the same benchmark and data for verified comparison. And here is the references that I have used for the article.